Good day to Dr. Kelvin and Dr. Angela. Welcome to the seminar presentation of the Sustainable Urban Wastewater Management Project, presented by Gregory, Isaac, myself Jonathan, Fidelis, and Ali Hamza. An overview of the presentation. The first milestone, milestone A, will be done by me. Milestone B, presented by Gregory and Fidelis. Milestone C, by Isaac. And milestone D, by Hamza. Firstly, our team has been appointed by the Kuching Water Board to design a recycled water supply system for the residential and industrial areas in Kuching City. Mainly, our area of concern will be located in Matang Jaya. Our findings and design will then be divided into 4 sections, which will be known as Milestone A, which is the preliminary design, and then Milestone B, whereby we assess the environmental impact, and Milestone C for a more detailed view of our detailed design, and then Milestone D, where we highlight on the cost implications of the project. First off, I will kick off this presentation by presenting Milestone A, which is the preliminary design. Our main objectives for this project is to find the best and most suited pipeline route from the wastewater plant to the proposed area at Matang Jaya. We are also to calculate the current wastewater generation and also to find out the current water demand from our current location. We are also to calculate the water demand for the fire hydrants and also to design a storage tank which can accommodate the water demand and to be placed in a suitable location. We are to analyze the existing ground elevation for the pipeline routes to determine locations of scour and air baths which will be placed along the pipeline. The expected life of our project is projected to be 10 years. Based on the projected water demand after 10 years, it is to be 13.35 megaliters per day. And from our calculation, the reclaimed water supply will be able to supply up to 16.63 megaliters per day. First off is our proposed pipe route 1. The total length of pipeline 1 will be approximately 2.6 kilometers. Branching out from pipeline 1, there will be 2 other pipelines, which are pipeline 2, which is approximately 1.5 kilometers, and pipeline 3, which is approximately 1 kilometer. Highlighted are the type of residential along the areas. This is our proposed pipeline route 2. From the beginning pipeline of pipeline 1 to the end of pipeline 1 is approximately 5.4 kilometers, and the beginning of pipeline 2 to the end of pipeline 2 is approximately 4.6 kilometers. These 2 pipelines will surround the areas of concern within our project. Also highlighted the type of residential and industrial areas within the area. From the areas that we have highlighted, we have classified each areas to a suited population equivalent. And from the population equivalent, we will obtain the total population equivalent, known as the PE, for the entire area that we are looking at. So the total PE for entire area of concern is 30,500.87. For the wastewater generation estimation, it is estimated that the population equivalent is approximately 30,500.87. The pipe length measured from Google Earth is estimated at 2.685 kilometers. Only a total of 75% of the total wastewater which have been collected can be reused. The assumption of pipe diameter used will be 1000 millimeters. The amount of water estimated which will be supplied to the entire site is approximately 16.625 megaliters per day and 7,410.1 megaliters per year. For the water demand, we have derived our calculation from the type of residential or commercial area. The MWA guidelines for areas which are shophouses are to be regarded as a sea level risk which requires a design flow of 1,140 liters per minute. We have highlighted the entire water demand of the area that is stressed. Firstly, flat and condominiums, double-story residential, single-story residential, double-story shophouses, triple-story shophouses, institution, and industrial areas which are considered light industrial areas. And we have highlighted the project boundary on this map. From the calculations, we have came up with the type of category of the building itself and the number of units. From these, we have derived the daily consumptions from each category and came up with a total of 7.93 million liters per day. For the water demand for fire hydrants, we have created a plan which highlights the areas that are to be placed with fire hydrants, which are roughly 90 meters apart. There will be approximately 51 fire hydrants proposed within a 90-meter radius around the buildings and houses. Due to the fact that because not every day there will be firefighting, therefore we have clustered all these areas into 6 clusters to reduce the intended water demand for fire hydrants. The water demand for fire hydrants for the 6 clusters is calculated to be 0.265 million liters per day. For the total water demand, we have derived the total daily consumption from the residents within the entire stress area, and also calculate the total water demand for the fire hydrants, which came to a total of 8.195 megaliters per day. From 8.195 megaliters per day, we have projected our expected water demand to 10 years, which will total up to 13.34879 megaliters per day. For the water storage tank, we have designed based on the minimum elevation head of tank, which is 5 meters, and is designed to be able to cater up to 13.35 megaliters per day. We have also allocated an additional 33% space for extra water storage. Therefore, the approximate size of water storage tank is to be 5 meters in height and 68 meters in diameter, or tanks of equivalent. For the longitudinal profile of pipe route, the total pipe length is approximately 2.685 meters. The data is obtained from Google Earth Pro and then converted and regenerated using AutoCAD Civil 3D. There will be a total of 7 air valves to be proposed on the higher points of the pipeline route, and total of 6 scour valves to be proposed on the lower points of the pipeline route. The longitudinal profile from channel 0 to channel 700, there will be 1 proposed air valve. From channel 700 to channel 1004, there will be 1 proposed air valve and 2 proposed scour valve. From channel 1004 to channel 2001, there will be 2 proposed air valve and 1 proposed scour valve. From channel 2100 to the end, there will be 3 proposed scour valve and 3 proposed air valve. Please note that the proposed pipeline is to be buried approximately 1 meter below the existing ground. Otherwise, if it's above ground, it is only for crossings or bridges. We will now move on to milestone 2.
Thank you, Jonathan. Moving on to the next section of this presentation, where the expected environmental impacts in this design project is discussed. The EIA, which is the Environmental Impact Assessment, is adopted in this project to minimize the environmental impacts. EIA is the study of identifying, predicting, evaluating, and communicating information regarding the impact on the environment by the proposed project, as well as to outline the mitigating measures before project approval and implementation. Moreover, this tool allows for potential problems to be detected early within the earliest stage of construction, which is the project planning and design stage. This leads to a large reduction in risk, translating to reduction in cost in the project implementation stage. Without further ado, this section will be divided into 4 parts, where I myself will cover the environmental impacts during investigation stage and construction stage, while Mr. Fidelis will cover the environmental impacts during the operational stage, as well as the impacts of abandonment of project at any stage. According to the statistics, 80% of the problems encountered on construction projects are due to unforeseen ground conditions. Hence, let's move on to the first environmental impact, which is during site investigation. First and foremost, soil erosion. In order to obtain information below the ground, borehole rigs are used to puncture the ground to obtain the ground data for geotechnical analysis. Borehole rigs are considered as a big machinery which is of a higher loading than typical vehicles on the ground. As borehole machineries are of high loading, the impact on the existing ground is significant enough that on softer ground, it would cause soil erosion around the area where the borehole rig moves through. Therefore, to mitigate the issue, Boreholes cannot be done too close to each other as it will weaken the ground as most of soil is bored out of analysis. Moving on to the next environment impacts during site investigation, which is water contamination. Wash boring rigs are used to extract soil samples for geotechnical specialists to further inspect what is beneath the existing ground. Wash boring rigs utilizes water to wash down the wash pipe, and water will disperse out between the wash pipe and the casing. The water which displaces out are mostly water with soil. This water will be discharged to the surrounding of the wash boring rigs, allowing it to free flow into lower grounds, hence flowing into nearest drains or rivers, which eventually cause water contamination. As for the remaining impacts such as the noise pollution, disturbance of flora and fauna, as well as social impacts, will be further discussed in the final report. Moving on to the next subsection of this presentation, where the environmental impacts during construction stage is discussed. Therefore, the environmental impacts will be divided into three parts, where the physical, biological, and human impact will be presented. Again, soil contamination. The main cause to this problem is when the soil is exposed to PAH and TPH from machine emissions. Therefore, the issues can be mitigated by following suitable procedures and rules or by disposing contaminated waste in an authorized landfill. Next, soil erosion. The issue is mainly attributed from the removal of topsoil from heavy machineries. Hence, one of the solutions is to plant vegetation with fast-growing species. Next, water pollution. Erosion caused by land removal may result in sediment and silt-bearing runoff contamination. Therefore, garbage disposal should be prohibited along any watercourse or on any vacant land on the property. Lastly, noise pollution. This is often generated by the operation of heavy machinery, equipment, and vehicles on site. Workers on site especially should wear hearing protection such as earmuffs or earplugs. Next, biological impact during construction will be discussed. Firstly, loss of flora and fauna. In the event of pipeline construction, land trenching causes the ecosystem to be highly disrupted. Therefore, contractors should consult and refer to relevant authorities before conducting any activities that require landscape alteration. Moving on, there will be an increase in BOD values. According to APEC, urban runoff also contributes to increase in oxygen demand. Therefore, it is important to ensure proper water flow into the appropriate channels. Wastewater from construction sites should avoid having direct flow into nearby bodies of water. Lastly, humans will also be infected during the construction stage. Firstly, health and safety. Workers or even residents live nearby are exposed to various common health problems such as airborne dust. Therefore, any person on site should always be wearing the PPE and be briefed on proper safety ethics. Next, settlement of population. In larger pipeline projects, houses that obstruct the proposed pipeline pathway might have to be relocated to move forward. Hence, it is important to properly plan the pipeline pathway to avoid intruding the lives of the residents in the nearby area. Moreover, this project will also benefit the economy. The construction of pipelines contributes towards government revenues as an increase of sales from the operation in supply chain industries, including machinery and steel. That's all for my part. I'll pass the time to Fidelis. Thank you.
Thank you, Gregory. My name is Fidelis Chung, and now I'm going to present the environmental impacts during the operational stage. Firstly, nutrient pollution. Wastewater plant can generate high amount of effluent like phosphorus and nitrogen if not maintained properly. High dosages of phosphorus and nitrogen will cause eutrophication that allows the excessive growth of algae, which eventually will lead to degradation of the aquatic ecosystem. This poses a threat to aquatic life. Affected aquatic life will slowly disappear in the affected area over time due to poor ecosystem quality. Now moving to the mitigation methods for nutrient pollution. Firstly, regularly monitor and test the water content level of phosphorus and nitrogen so that it does not reach a high concentration so it can cause eutrophication. If high concentration of phosphorus and nitrogen are found, iron and alum can be added to combat the reduction of the concentration of phosphorus. Nitrate can be added to maintain high redox condition at sediment-water interface to prevent the internal loading of phosphorus. Now moving to the health impact. Wastewater contains pathogenic organism due to contamination of feces and other organic waste materials. Aside from that, production of harmful emission during the operational stage that includes carcinogenic emission, depletion of ozone layer, and inorganic material that could potentially cause respiratory problems. The main pollution throughout the entire operation lifespan is the production of carbon dioxide due to the byproduct of burning fossil fuel for energy. Aside from that, potential of fly and mosquito breeding grounds in sludge drying lagoons could pose serious health threats like dengue or malaria to nearby residents. Now moving to the mitigation methods, application of chlorination facility can reduce fecal coliform. Usage of renewable source of energy for the operation of the water treatment plant, like using solar energy. Lastly, adding calcium hydrochloride or chlorine to polishing pond or drying lagoon to minimize the breeding of mosquitoes and flies. Now moving to odor pollution during the operational stage. High sulfite content could result in the discharge of a moderate amount of potentially irritant odors. Furthermore, these circumstances produce a high corrosive environment for both collection of wastewater and treatment system. When the effluent appears black, it shows that the presence of sulfite and low oxygen level. Now moving to the mitigation methods for odor pollution. Sludge that are collected in the aerobic lagoons will be eliminated once every 2 to 3 years. The sludge is distributed into the sludge drying lagoons to be dried out in the sun. Once dried, the sludge is largely innocuous. Now moving to the risk of plant failure. There will be potential risks that the plant will face operational difficulties like plant startup or equipment malfunction, especially the equipment that delivers aeration to the complete and partial mixed lagoon. Aside from that, sudden disconnection of electricity will cause the plant from functioning normally. Now moving to the mitigation methods for risk of plant failure. All operators and maintenance crew have to be properly trained and ensure all spare parts are readily available so the maintenance crew can utilize the spare parts whenever necessary to keep the treatment plant running at an efficient rate. Backup and standby generators have to be built to keep the treatment plant operational if there is any power shortages. Ensure all equipments are properly maintained and are in a good condition to prevent equipment failure. All personnel involving the treatment plant should be provided technical assistance program to fully utilize their equipment and how to properly use them. As a result, equipments are less likely to break down. Now moving to the environmental impacts of abandonment of project at any stage. The table above shows a summary of evaluation of the impact if the project were abandoned at any stage of the project. There are a lot of environmental impacts if the project is abandoned, but these can be classified into 4 classes, which are high, medium, low, and non-impactful. Before any modification is done to the project, a proper investigation is done, and even during this stage, there are many environmental impacts, but they are mostly from low impact. Some are even low impactful. This increases to the upper level, which are moderate and highly impactful when the construction phase starts. In summary, from the table we can conclude that there are negative impacts to the environment during all stages, ranging from the investigation to the construction and the operational stages, with the most heavily impacted if the project is abandoned during the construction stage. That is all from me, and I'll pass to Isaac.
Thank you, Fidelis, for your presentation. Hello, my name is Isaac, and in my part, I'll talk about our findings in milestone C. The nominated pipeline route for our project will be just over 2 kilometers long, and the type of pipe material we'll be using is ductile iron cement line pipes, which is the industry standard for wastewater systems in Malaysia. These pipes are made up of iron carbon and then lined with graphic nodules during the solidification process. These pipes are very suitable to be used in harsh conditions such as underneath highways, deep trenching, and resistant to water hammer. The reason we chose the ACL pipes for this project is because it has twice the strength of grey iron, which is the predecessor of the ACL pipes, which means it has a higher impact strength and has bigger elongation. The pipes don't crack under local strain and internal pressure, and they have high resistance to lateral stress. Also, the pipes have low coefficient of friction, which means they lead to high flow capacity, low pump cost, and means low head loss. These pipes can also be considered as a lightweight material with low carbon footprints, which means it has less occupational health and safety hazards. The downsides to the ACL pipes are their high material costs. Pipes are very dense and heavy, so they require heavy machinery for transport and installation. Any temporary repair can lead to a permanent process, and to join these pipes, stiffeners must be used to ensure a smooth pipe connection. From the hydraulics analysis of our sewage pipeline, there are a few things that can be highlighted. Our estimated wastewater generated in 2023 is 0.403 cubic meters per second. From that, we will get a nominal diameter of 700 millimeters and a pipe flow velocity of 1.165 meters per second. The slope, which we calculated, can also be seen in the slide shown. Continuing the hydraulic analysis, we get a static lift of almost 9 meters, a minor head loss of 0.263 meters, a frictional head loss of 0.016 meters, and a pumping power computation of 36.27 kilowatts. In our proposed pipeline, stop valves will be implemented. Stop valves are used to open or shut the flow of water into the primary or secondary pipeline. These valves are mainly used for maintenance purposes, which are installed at the start of the primary pipeline and the secondary pipeline. So these valves are used to turn off the water flow when maintenance is required, as you can't do maintenance of the pipe when the water is still flowing. Our pipeline will also make use of reflux valves, which is to prevent water flowing back, which in turn help protect the pump. These valves are installed at a low point between the high level water tank and the water treatment plant. As for the hydraulic analysis of our reclaimed water pipeline, a few things to highlight. Our pipe flow rate is at 0.155 cubic meters per second, nominal pipe diameter of 400 millimeters, and from the losses occurred from elevated water tank to the endpoint, we have a major loss of 3.134 meters, a minor loss of 0.336 meters, frictional loss of 11.55 meters, all from the height of the structure, which is the water tank at 15 meters. We then started to calculate the major losses from wastewater treatment plant to the high level water tank. We get a major loss of 5.3 meters, a minor loss of 0.4 meters, a frictional loss of 0.09 meters. The head required by the pump will be 5.83 meters, and the pumping power will be at 12.64 kilowatts. From the reclaimed water analysis, we also can calculate the water hammer. For that, we have to first determine the celerity of wave, which in our pipeline will be 1291.675 meter per second. Pressure head due to the water hammer is 1.679 megapascals, which is less than the hydrostatic test pressure of pipes, which can be found in Appendix B in the report later on. For our pipeline, there will only be one proposed truss block for the 190-degree bend in the pipeline. This truss block must withstand around 72 kilonewtons of pressure, and from that we can calculate that the area of the truss block will be around 1.5 square meters. That is all from my part. I'll now pass on the presentation to Hamza. Thank you.
Thank you very much, Isaac. My name is Hamza Thaheem and I will be presenting Milestone D to the audience. In Milestone D, we have prepared an economic analysis of the pump and the pipeline for the determination of the optimum pipe diameter that should be used for the supply of reclaimed water and the sewerage pipelines. These calculations were done in 4 variations. The first calculations are for sewerage pipeline, sewage water pipeline, and then followed by the reclaimed water pipeline, and finally the running cost and the summary of costs. I will start with the capital cost for the sewage pipeline. The total length of the sewage pipeline from the collection area to the treatment plant is about 2,679.566 meters for a DICL pipe with internal diameter of 664.2 millimeters. The price is 1,466.40 ringgit for every 700 millimeters, totaling the cost of the pipeline to be 3,955,710.78 ringgits. Capital cost for the pumping station is 12,000 ringgit per kilowatt, with the required power being 36.227 kilowatts. Our total price goes up to 435,240 ringgits. There is only one generator house totaling to 250,000 ringgits. Price of a single shaft is 200,000 ringgits, and we have a total of 26 shafts at 100-meter intervals, totaling our price to 5,200,000 ringgits. Therefore, our total capital cost for sewage pipeline is 9,841,028 ringgits. The running cost is on a whole other level, starting with the operational and maintenance cost of 43,334.737 ringgits combined. Furthermore, upon calculation between 3 different tariffs for electricity, tariff 3 was selected, which amounts to 66,606.50 ringgits per year. This totals to 109,940.87 ringgit per year of running cost. Total cost for the reclaimed water pipeline also starts with the pipe type. For the reclaimed water, we have used DICL type with an internal diameter of 366.4 millimeters and a nominal diameter of 400 millimeters, which costs 521 ringgits per millimeter and runs for a total of 2.685 kilometers. This brings the total of the pipe to 1,398,885 ringgits. There will be only one wastewater treatment plant, which has a buying and installation cost of about 3,500,000 ringgits. After calculation for power had been made, it was estimated the cost of pump station would be 151,680 ringgits. From milestone 1, we also know that there are a total of 51 fire hydrants in the proposed site, which are 2,300 ringgits each, totaling to 117,300 ringgits. Furthermore, there is a generator house which costs 250,000 ringgit and an elevated storage tank which costs about 2,500,000 ringgits. We also have a total of 3 stop valves of cost 800 ringgit for each, with a total of 2,400 ringgits. We have a single reflux valve for 1,800 ringgits and a total of 5 scour valves at 2,200 ringgit each, with a total of 13,200 ringgits. There are 7 air valves on this pipeline for 1,500 ringgit each, totaling to 10,500 ringgits. And finally, from milestone C, we know our thrust block is 1.52 meter cube, which totals to 975 ringgits. Therefore, when we sum all of this up, the total cost for the reclaimed water pipeline comes to a total of 7,946,740 ringgits. The running cost is slightly less than the sewage treatment plant, with our operation and maintenance cost for trunk and rising main standing at 10,341.75 ringgits, and the pump station at 5,172.30 ringgit per year. Furthermore, tariff 3 was selected for our electricity charges, which amounts to 23,215.50 ringgit per year. This brings the total of our running cost to 38,729 ringgits per year. The renewal and adaptation cost for our pumps and pump station is 45% of the pump installation cost, which gives us a total of 68,256 ringgit. In summary, when we add all the capital costs for the sewage and reclaimed water treatment plant, we get a total of 17,537,690.78 ringgits. And upon adding the running costs for both the pipelines for operation and maintenance, we get a total of 58,848.42 ringgits. And for the electricity charges, we get a total of 89,822 ringgits, summing up the total running cost to 148,670.42 ringgits per year, and the renewal cost at 68,256 ringgits respectively. This brings our initial year cost to a total of 17,754,617.2 ringgits. A cumulative cost for the first 10 years is estimated at 19,923,881.4 ringgits, and for 20 years it is estimated at 22,093,145.6 ringgits. In conclusion, we were tasked to design a recycled water supply system to residential and industrial areas in Matang, Jaya, Kuching. Life cycle was supposed to be 20 years with a DICL lifespan of 100 years, but it is limited due to the limitation of water pump pipe life. The total PE is 30,500.87 with a total daily water consumption 8.195 million liters per day, including that of fire hydrants. The estimated length of the pipeline is 2.679.566 km for sewage pipeline and 2.685 km for reclaimed water pipeline. After a detailed calculation, the estimated price of the project is 22,093,145.6 ringgit. Thank you very much.